Okay, so in a previous lecture, we talked about using the first derivative to find relative mins and relative maxes. And the first derivative helped us to determine where the function was increasing on its graph or decreasing on its graph. In this particular lecture, we're going to be talking about the second derivative and helping us to classify minimum and maximum values. Now, the second derivative is going to help us with this thing called concavity. But before I actually get to that, which is the theorem that we're going to do right after this, let's talk about the definition of concavity. Suppose that f is a function whose derivative, the first derivative, exists at every point in the open interval I. Then f concaves up on I if the first derivative is increasing. So if the first derivative is increasing, then it's telling you that the concavity goes up. This says f is concave down on I if the first derivative is decreasing. Okay? This is a very simple definition of concavity. Think of it like a cup. It's either concaving up or it's concaving down. Got it? Okay. The next theorem actually explains concavity a little bit better by looking at the first derivative as well as the second derivative. So stay tuned. All right, so let's look at this theorem. This theorem says it's a test for concavity. So let's look at number 1. It says if the second derivative is greater than 0 on an interval I, then the graph of f is going to concave up. The second part says if f double prime, so the second derivative of f, is less than 0 on an interval, then the graph of f concaves down. Now we're going to put those two derivatives together. We're going to put the first derivative together and the second derivative together. And I'm going to put them together in this little chart. Because remember, the first derivative tells me if it's decreasing or increasing. The second derivative says if it's concave down or concave up, right? So let's make sure we have that straight. First derivative tells me if it's increasing or decreasing. Second derivative tells me if it concaves up or concaves down. So make certain you have the two of those derivatives straight. Got it? Okay. So let's look at the first derivative when it's decreasing. So it's going down, right? Decreasing means it's doing this number, isn't it? So if the first derivative tells you your graph is decreasing, and your second derivative says it's concaving down, so it's decreasing and it's concaving down, which means it's doing this number. With me? Okay. If it's decreasing and concaving up, then it's doing this number. Decreases, but it's concaving up at the same time. Right? See the opening? See how it goes up? See this? See how it's going down? Right? That curvature? With me? Okay. Now let's look when our first derivative is increasing, because that means it's doing this number when it's increasing. If the first derivative says my graph is increasing, and my second derivative says it's concaving down, right? So that means it increases and it cups down at the same time. Boop. That makes sense? If your first derivative is increasing and the second derivative says it concaves up, that means as it's going up, it's cupping in the up direction. Make sense? Okay. So you're like, okay, how do I keep that straight? Remember, less than 0 on the first derivative means it's going down. And notice, the second derivative, when it's less than 0, means it concaves down. Right? So first derivative and second derivative, when they're both less than 0, we've got this decrease and this cupping down thing. First derivative, when it's greater than 0, does this going up. And the second derivative greater than 0 means it's like cupping up. With me? I like to use because I'm a visual person, so I use my hands to visualize the cupping up or the cupping down, so to speak. That's my terminology. Does that make sense? Okay, stay tuned. I got another theorem for us before we get into some examples. I'll be right back. So let's look at this next theorem. This theorem is the second derivative test for determining relative extrema. So we have the first derivative test, and now we have a second derivative test. So just hang in there, because some of you are going, oh my gosh, which one do I use? Just relax, okay? We'll get there. Let's look at this theorem about us using the second derivative to determine a relative extrema. Suppose that f is differentiable for every x in an open interval ab, and there is a critical value c in that interval ab, for which f prime of c is equal to 0. So I'm going to stop right there a second. So notice when it tells me for which f prime of c equals 0, it's still telling me that to find the critical value, I am going to have to use that first derivative, set it equal to 0 so I can find the critical value. So this part's not changing. To find my critical value, I take the first derivative, I set it equal to 0 so I can find the number that actually makes the first derivative 0. So that's not changing. Got it? Okay. Now, after that, based upon a previous lecture that we did, after we found that critical value, we started graphing to determine if it was increasing or decreasing, didn't we? This theorem gives me an option. Instead of determining if it's increasing or decreasing by using the first derivative, I can actually use the second derivative to help me determine that, if it's a relative min or relative max. Got it? So here's the deal. We find the critical value like usual. And here's where we change it a little bit if we want to. Remember, after we found that critical value, we plugged that critical value into the original function and found the y value, didn't we? This is the y value. And it's telling us the y value is a relative minimum if the second derivative at that number is greater than 0. Okay, so remember just a few minutes ago we looked at that theorem number 4. If your second derivative is greater than 0, remember, second derivative tells me if it concaves up or concaves down, right? If your second derivative is greater than 0, which direction does it concave? Yeah, if it's greater than 0, then it's concaving up. Can you see that this would be a relative minimum? It's almost like the bottom of a parabola, right? Okay. If, right, there's that y value again. After you found the critical value, you plugged it into the original function and found the y value. If this y value, or this y value is going to be a relative maximum if the second derivative at that critical is less than 0. Remember, second derivative tells you the concavity, and if your second derivative is less than 0, then which way does it concave? It concaves down. Do you see that that's like the top of a parabola facing down? Do you see how that could be the relative maximum? Okay. Got it? All right. Now, if you take the second derivative and equals 0, 0 is neither positive nor negative, is it? Okay, which means if your second derivative, when you plug in that critical value, actually equals 0, then I can't use the second derivative test. I am going to have to stick with the first derivative, plug numbers into the left of the critical value, plug numbers into the right of the critical value, and see if it's increasing or decreasing, and that will help me find a relative min or relative max. Okay? That's what this last part is telling us. If my second derivative at that critical value is 0, 0 is not positive or negative, so I can't tell any concavity, so it's not going to help me. Which means I need to stick with the first derivative and figure out where it's increasing and where it's decreasing so that I can determine a relative min or max. Got it? Okay, so stay tuned. I got some examples for us. All right, time for some examples. Let's look at the directions. Find all relative extrema and classify as a min or a max by using the second derivative test. Okay, but the point is they're asking us to find all relative extrema, correct? So based on a previous lecture, how do you find the relative extrema? How do you start? What do you need to find first? Good, the critical values. How do you find the critical values? Ah, yes, the first derivative. Great job, you guys. Good memory. So first, we need to find the first derivative, because what does that lead to us finding? The critical value. Okay, so the first derivative is going to be 24x squared minus 6. Yes? And then what do? Yeah, to find the actual critical values, you've got to set that first derivative equal to 0, don't you? So, we set it equal to 0 and we solve for x, correct? So, right now all this is algebraic stuff, right? Algebraic steps. And if you're like, wait, how'd you get 1/4? I divide both sides by 24, correct? So 6 over 24 reduces, doesn't it? Yeah, there we go. Okay, so then you got to get rid of that square by taking square root. Okay, but remember something. This square means you're going to get how many answers? Good, 2 answers. So the square root of 1/4. Most of you are saying it's 1/2. That's true. But it's not just 1/2. It's also negative 1/2, because you're supposed to get 2 answers. In this case, a positive 1/2 and a negative 1/2. Right? Okay. Now what's next? After you find, well, I should say, these two numbers are my critical values, a negative 1/2 and a positive 1/2. And now what? Yeah, you need to find the y values that go with them, correct? So, second, find the y's, right? Find your f of x's. So, in this case, you're finding how many y's? 2. So the first one is x equaling negative 1/2, so I'm actually finding f of negative 1/2. And if you plug everything in, which you should do prior to doing any calculator punching, and I'm going to be honest with you, I hope you're not calculator punching. All right, whoops, almost forgot the third power there. So negative 1/2 to the third power is negative 1/8 times 8, negative 1, plus the 3, right, plus the 1. So I get 3. Did you? Which means we have this point of negative 1/2, comma 3. Got it. Now, we have the second critical value of positive 1/2. So to find the y, that's right, plug it in. And to the power of 3, right? Okay, so now what? Yeah, this is going to be 1 minus 3 plus 1, which, negative 2 plus negative 1. Good, which means we just found the point, positive 1/2 and negative 1, didn't we? Okay, and now we've got to figure out if these are relative mins or maxes. Now, in a previous lecture, we would start graphing and finding where it increased and decreased, correct? These directions say, though, they'd like you to use the second derivative test instead. So step 3 from a prior lecture was finding where it increased or decreased. In this case, that second derivative test is not finding where it's increasing or decreasing. Our third step here is finding where it concaves up or down. That's the second derivative test. Got it? So we're replacing the first derivative test, finding where it increases and decreases, by using the second derivative test of concavity. So, in this case, we have to find the second derivative, don't we? Here's our first derivative. What will our second derivative be? Good, 48x. And now, that's right, x is the critical value. So we have to plug our critical values into here and see what's going to happen. Now I need a little bit of board space, so I am going to be doing some erasing over here. You understand what we're doing, right? We're doing the second derivative test, which means we have got to plug our critical values in and find where it's concaving, up or down. So I'm going to bring our work up over here. And the first thing I am going to look at is the second derivative at one of the critical values of -1/2. So when I plug it in, we get -24. Now, -24 is less than 0, isn't it? Since it's less than 0, which way does it concave? Yeah, less than 0 means this one concaves down. So I'm going to draw myself a picture. So if it concaves down, do I have a relative min or a relative max at the -1/2? Relative max. Good job, because it concaves down, right? So we have a relative max at y equals 3, and it occurs at x equals -1/2, because that's that point, isn't it? Good? Okay. But we had a second critical value. So now I've got to find the second derivative at the +1/2. So we have 48 times the 1/2, which is a +24, yes? And a +24 is greater than 0. So since it's greater than 0, which way does it concave? This one, because it's positive, right, concaves up. So I'm drawing myself a picture. So if it concaves up, very good, you have a relative min, don't you? So I have a relative min at y equals -1, and it occurs at x equals 1/2. Cool? With me? Second derivative test, there's no graphing. The second derivative test is you finding the second derivative, plugging your critical value into it, and if it turns out that your answer is less than 0, it concaves down, which means you have a max, right? Because it would be at the top. And if it turns out to be greater than 0, that means it concaves up, which means you've got a min. Good? Hang in there. Got another example. Let's look at this next example. Still asking us to find the relative extrema. So what do we do first? Yep, find the first derivative in order to find the critical value. Okay, so first derivative looks like, good, -10x plus 8, and then set it equal to 0 so you can find the critical value. So when I do this, looks like I get 4/5 after I reduce my fraction. Do you agree? Wonderful. Then what? Find the y value. Excellent. So second, we are finding y, or the f of x. So we're taking f of +4/5, aren't we? And we are plugging it in to that thing. Now, I know some of you are like, fractions! And I get it. But here's the thing, they're really not as bad as you think, right? You have to know how to work with fractions. Don't let the calculator do all the work for you. First thing you're going to do is square that, which is 16/25, right? And then 32/5, because when you multiply, minus 7/1, right? That 5 and 25 cancel, don't they? Good, so I have a negative 16 over 5 plus 32 over 5. Make that 7 into a fraction that also has a denominator of 5. So that's negative 35 over 5. Excellent. And so, when you work this all out, I don't know about you, but I get negative 19 over 5. Do you agree? Lovely. And you got it on your calculator. Fine. But you got to know how to deal with fractions. They don't go away. And you're like, my calculator doesn't go away. Well, what happens if your calculator's battery runs out? You're going to have to know how to deal with fractions without the calculator sometimes. All I'm saying. Okay, so here's the point we have. We have the point 4/5, comma, negative 19 over 5. Okay, now what? Yes, since they want us to use the second derivative test, we are now determining concavity, right? Is it up or is it down? First derivative test deals with increasing and decreasing. Second derivative test deals with concaving down or concaving up. So I have got to take that second derivative. So here is my first derivative. What would my second derivative be? Good, a negative 10. So we only have one critical value, don't we? So in this case, since x equals 4/5, and we plug in that 4/5, well, here's the deal. Do you notice there's no x here? So since there's no x here, this is a constant, isn't it? So even though you're plugging in 4/5, you're just still going to get a negative 10. Agreed? Which means that's less than 0. And so since it's less than 0, this concaves down. So since it concaves down, I'm going to draw my picture. That means we have a relative max. Right? Because it would be here at the top, wouldn't it? So we have a relative max at y equals negative 19 over 5, and it occurs at x equals 4/5. Perfect. Hey, I got a constant. Yay, that helps us out. With me? I don't have a whole lot of plugging in to do in this case. Cool? Okay, now the second derivative test will actually help me find another piece of information about my function besides relative mins or maximums. So stay tuned, and I'm going to be talking about a theorem.